48. 48. 48? 6'2"?
I mean, you explained it, and I could.
I didn't really explain it. I sort of gave you an idea of what to try. Let's see. Ooh, I like it. It's too bad. Basically, I have that. The height H, lower base R. Cool. So, there's a couple different ways to do this. The most direct way to do this problem, now I think you and I, we were talking about number 49 at one point. How do I say this? What's the area of the base? What's the area of that top? Pi little r squared, I like it. And then isn't everywhere in between also its own circle? Isn't that sort of the whole idea? So
like axis, so we.
Yeah, so you can put your axis anywhere you want to. So I would put it there. Even here, right? I like it. Let me stop there. Is that okay? I should have probably done that in a different color. Too bad for us. So, what do I? Let me see. How do I say this? So this is my region. So now unrotate it. Like close that weird thing that I came in the other day, and it just becomes this shape here. That's what's been rotated to make that. Is that? Do you guys see that? Okay.
Yeah.
Go on. Okay. So this. What's this?
That's the height H.
Oh, I see. This is H. This is R. Little r. This is.
R.
Like, let me stop there. You guys see that? Because the thing on this axis tells me how long this is. So when I said what's this, I know why I said H, but what's this is R. This is big ass R. This is H. I like it. Okay, let me stop there for a second. So I got no numbers here. Too bad for us. But now I'm going to rotate this around the y-axis, right? And what section are we in? So you say there's no question about which method to use because we're in section 6.2 before we even knew shells existed. So we're going to use discs. That kind of makes sense. This is a bunch of circles added together, right? So if I'm going to rotate around this, what do I want? And in fact, what am I? So if I take an arbitrary place for a disk, and it's going to be exactly like you'd hope it. There's a disk right there. So I'm going to find my disks up and down the y-axis, right? So it's going to be integral d what? Let's start there. Because I'm rotating around the y-axis, so it's going to be integral dy. Right? So what is it that I need? What's my radius going to be? No. So when it gets up here, my radius is little r. When it gets down there, my radius is big R. I need to know what my radius is in general. So what do I need to know that I normally am given that I actually have to figure out for myself now? What's the definition of that? What's the equation of that line? Let me stop here for a second. We normally are given that, right? Where it's one of the boundaries that they give me the equation for. Is that correct? That's normally what I'm given. And then I have to kind of figure out some of this other things. My range for my dy, what's it go from to. I got to figure that out. Now they gave me all the ranges. They just didn't tell me the most important damn thing. What is this? That's what tells me what my radius is. So it's some arbitrary position in between these two. I know what it is here. Big ass R. I know what it is there. Little ass R. What is it anywhere in between? Oh shit, it's whatever that is. It's whatever that function is. So how do I get that function? What points does it go through? What's that point? Be very specific. Be very specific. No, I got too many R's. There's a little R and a big R.
Oh, little r.
There we go. Little R, H. What point is that? Big R, 0. Can you find the equation of the line going through those 2 points? The answer is yes. Even if you can't, I'm going to pretend like it's yes. Right? How do you find the equation of the line through 2 points? Easy. I don't care that there's no numbers. I don't give a shit. What do you need to find the equation of a line? Slope. All right, slope is a good place to start. Yeah, it'll be H over. Alright, it's H minus 0 over little r minus big R. That's the slope. And already I can tell some of you guys are like, screw this wrong. But this is, dear God, you have got to be able to handle no numbers by this point. I mean, come on. So I got my slope. What else do I need? A point. Alright, so then I can do y minus y1 equals m. I'm going to pick the point that's got a 0 in it. So y minus 0 equals m times x minus r. Ooh, that looks yummy. I like it. So, I mean, and what do I need this in terms of? So I need to solve this for x, right? I like it. I like it even more. So I get y times r minus r divided by h plus big S r. I mean, come on, that's multiply, divide, add. No big deal. Again, no big deal. So that's what this is. That's this. That's this here. So what's my radius going to be? There's too many freaking r's all over the place, but what do I call this? Let's call it R. D for our disk. Our disk is going to be this. And you're going to integrate from what to what?
From
0 to h pi r squared. I like it. So you're just going to put that in there. Okay, so I've got this set up for you. Was that easy? No, not really. No, I agree. It wasn't. But you have to start with, what would I rotate to make this picture? Right? Because that's the whole thing. What's the region that I would rotate to make that picture? They give you tons of examples, actually, with exactly that idea. Cool. Not tons, but a few. I mean, now it's just, what's your only variable going to be in here? Y. So, I mean, what's this? A number. That's a number. Who cares? So when you integrate this, well, you got to square it. Ooh. So you got to FOIL that thing out. This is just an exercise in dealing with the fact that there are no numbers here.
So should we bring the y in and that's where?
Well, I mean, not really. To be honest, what I would do is I would call this whole thing C. Is that cool? Because that's just one big constant, right? So I'd say, let C be R minus R over H. And that's going to make this look a lot better. So now it's CY plus R. Oh, so you can do that anytime you want to. You have a big-ass collection of a bunch of constants. These are all just constants. So together they make one constant. But at the very end, you just plug back in what C was. But it's the same thing, just looks easier. I like it.
Big R is a constant too, right?
Yeah, big-ass R is a constant. But I mean, at that point, I just leave it. There's no reason to mess with them. And so now square that, and then you can. And in fact, let me see if you guys. I can integrate this directly without squaring. Because it's basically linear in size, except for the c, right? So this would be cy plus r cubed over 3 c. Because you want to kill that c that wants to come out for chain rule, right? Or you could square it and do it that way, and you basically get the same thing. Just you'll have it all multiplied out. Yeah.
Where did you get the x minus r? Y equals slope.
Yeah, what are my 2 points? Little RH and big SR 0, right? So y minus, and I picked the point with the 0 in it. So y minus 0 equals m x minus r, the x piece. Right? It's the y piece and the x piece. Cool. I like it. Cool. Alright. Let's not focus on that problem, actually, because I'm not going to give you one like that on the test, to be honest. But I just want to, that's the kind of thing that everything's gearing up towards, is for you to take something that doesn't have its own coordinate system set up. I mean, you got an object sitting in space. It doesn't have a coordinate system on it, so we put one on it. Because we're totally allowed to. If I put this coordinate system up here, as long as and then I can find the equation of the line, now it's going to be based on the x-axis being up there, it would look different. My answer comes out exactly the same. The answer is going to come out exactly the same. But so why put my coordinate system somewhere funky? Let me put it where it makes the whole thing easier. So that's, in reality, you can put your coordinate system wherever the hell you want to. The minute you do that, the math doesn't give a shit. So we put it somewhere where it's easy to define what's going on. So that's a big thing to get out of this kind of problem, is there's no coordinate system. Oh shit, well then put it anywhere you want to. All right, I'm going to put it here, because then my radii are really easy, and then the axis of rotation is the y-axis. That makes it easy. It's when they give me a coordinate system that already exists, I'm like, oh shit, I would have put this over here. Oh well, too bad.
Is the test on chapter 6 only?
I forget. No, I actually honestly forget.
5.3 to 6.5.
Yes, because the last test went up to 5.2. I couldn't remember where in chapter 5 we left off. So, I mean, this starts from when we first talked about definite integrals, indefinite integrals. It goes through U substitution, right? Yeah.
5.4 number 4.
Oh, okay. 544?
Yeah.
Okay. So this one tells you to verify that this equals this. Okay, so first thing I got to say is, I know it's obvious, but you have to show me anyway. I'm so joking. That is so desperately not obvious. I mean, the one thing that is semi-obvious is, for example, what is the integral of 1 over square root of x? Does somebody know? That would just be the integral of that, right? So help me out. What would that integral be?
-1/2 x to...
You're thinking differential.
2x.
So it'd be x to the positive 1/2, because you add 1.
Into.
Divided by that is times 2. You're thinking derivative, yeah. So look here. Isn't that there? Isn't it over square root of basically x, just with some... And look what the answer has in it. The square root of that stuff. So, I mean, so that part looks right. So I don't know if the question is, do you understand what they want you to do here? You cannot integrate this. Well, you could, to be honest. But you don't have to. The problem just says verify this is true. So how do I verify that the integral of something is a function? I take the derivative of this and show that it equals that. And derivatives are a hell of a lot easier than integration, right? Like they're supposed to be, because integration takes derivatives, which are difficult on their own, and turns it backwards. How would I...
Is that like 3 pieces in a product? Yeah.
No, it's... one function and another function. Because what are the parts that have x in them? That doesn't have an x in it. That's a constant.
Oh.
So that's part of this function. So product rule would be f prime g f g prime. And of course the plus c goes away right off the bat.
How does it work out if there's three things being multiplied?
Oh, so so if I have an FGH, it should be F prime GH plus FG prime H plus FGH prime. It's just that everybody gets a term. So I can extend the product rule remarkably easily, just give everybody a term. So 3 terms, we'll end up with 3 terms. It's kind of nice. 3 functions, 3 terms. 4 functions, 4 terms. I like it. Yeah.
Also 18.
I was going to say. Oh, real quick, before I go away from this. What method would you use if you had to integrate this? The runaway screaming method. No, that doesn't. See, probably the only method we have, USUB, right? So if I let u, what would you let u equal?
A plus B.
A plus bx. Good, not the radical. That's And what would du be?
B.
B.
Yes.
dx. I like it. So all I'm missing is a b, right? But what about this guy? So if u is a plus bx, x is u minus a divided by b. And this would work. So at first I said you can't, and then I realized, yeah, we actually could. It's only a u sub problem, but you don't have to. You don't have to. You just have to take the derivative and show it equals that. That verifies that the integral is that. Okay.
How would you get the b?
Or 1 over b. Right? And then this I would replace with that. And the reason this works is you know, if I have this problem, why is this problem really easy? I don't have to. Why can I do that really easy? Because the bottom is a single term inside, so I can make the x to the 1/2 and then break it up, and no big deal. So once I let this be u, it'll just be a single term inside, and then I can just split it up across the top. The top will now be a couple terms, but who cares? I can just split it up. It's doable, completely doable. Okay, cool. Thinking about what problems have been on the test now. Very interesting. What's up? I did. Didn't I? What's up?
As a test.
Oh, that's what's funny. All right. Where else do we want to go? Anywhere? Do we not want to go? Yes.
18.
18 and 5/4. Oh, this is. I think we talked about this one, but it's. What's one of the major themes of my semester here? Apparently. There it is. Yeah, simplify. So you gotta know trig, which is why it's a prerequisite. Sine 2x, the identity is 2 sine x cosine x, and then one of the sine x's can, and then it's easy. Is that cool?
Yeah.
So what's the question?
I can remember this.
Oh, okay. So now, yeah. So it'll be 2 sine x cosine x, sine x. So now it's just 2 cosine x. You got to integrate. What is the integral of 2 cosine x? What's all these negatives?
No, fine.
2 sine x. Let's see. It's when you take the derivative of cosine is negative. So the integral of cosine is not negative. I know cosine and sine suck. I can hear changing gears up in your brain, but right, you think to yourself, if I took a derivative, would a negative come out? No. Derivative of sine is cosine, so I don't have to put a negative out there to handle that because there's no negative to handle. As you integrate, you should be thinking backwards at the same time. Does it make sense what I'm writing? If I took the derivative, do I get this? That's what you should be thinking as you write stuff down as the answer to an integral is the derivative coming out to what it was? Okay, yes, okay. Maybe. I mean, that's how you do it. By the way, if you are considering what to focus your time on, if you have trouble with U substitution and you have trouble with the shell method, pick U sub to review. That's much more important, to be honest. Why do we spend so much time on the other stuff? Because they involve integration, which is review, plus it's really freaky. Right? It takes a while to really understand what's going on. It doesn't mean I'm going to have a lot of problems like that on the test. It just means it took a long time to figure out what the hell's going on. U sub is the more important skill to have. It is the more general skill to have. Right? If you're going to take Calc 2, you got to know U sub or you're dead coming out of the gate. So if you have trouble with U sub, focus on that. Right? Okay. Where did I put that? Okay. Where do you want to go next? Home. Yes.
I just wonder how to do that 64 6.2.
Oh, okay. That one sounds very involved. So find the volume common to two. So you got two circular cylinders, each with radius r. If the axes of the cylinders intersect at right angles, and I guess they're trying to give us help with these pictures they give us, but that each with radius r. If the axes of the cylinders intersect at right angles. So I guess they're the same shaped cylinder, each with radius r. Okay. So you'd have another cylinder coming in. How can I draw this? Yeah, like coming out the center here, going in, right? So you'd have to find their points of intersection first. Let's see. So if you think about it, I mean, the picture, you can almost break it apart. So you've got one soup can there, you got another soup can there, and they're talking about the volume of soup that each one shares, right? So there's parts. So my picture is obviously horrible, but too bad. The computer generated one is probably a little bit better. You want to figure out. There's two ways to try to think about figuring it out. There's parts of the volume that they're left out that's not included in both. So you think, is that a good way to go to try to figure that out? Or to try to figure the points of intersection to get the inner region. What's the inner region look like, right? I don't think that's one I assigned, though. Is that right? Did I assign? Okay. So it's maybe a little much to go into at the moment, right? But you want to try to figure out, is there... they kind of give you a little hint, because you can see, I can't recreate what's in the book, but you can see the intersection point is the lines of intersection on the top. See where the blue's in the middle?
Yeah.
You might want to try to define what those boundaries are, because it's all about finding the boundaries of a region. And there's all kinds of symmetry in this thing, so you can. There's a lot to this problem. Is what I'm trying to say. But you try to get slices and try to get some of the rotation out of the way, like we did with that weird trapezoidal thing. So you can identify what the region looks like inside. But that's all I'm going to say for right now. Yes.
I read this question. 5.3, number 9.
Oh, okay. Okay. This is like number 5. Was it 5 on the practice test? I'll do the one out of the book, and then I want to do that one too, because I didn't put it on the answer key. Right? Doesn't the last problem on the practice tests ask you to find a derivative of an interval? I think I gave all my practice tests away. Here it is. Yeah, number 6, sorry. And number 6 is actually kind of gross. But here's the one out of the book. You said number 9?
Yes, 5.39.
So this one looks like this. Is that what it is? Oh, g of x, okay. That makes more sense. C minus 2 squared. Alright, so this, you just got to remember, why is this one going to be relatively easy? What is the true variable of this function? S, good. This exists. This complete function just exists. So the variable is s. It's how far along that function I'm going to see the area. So as I increase s, I'm getting more and more area of that function that just sits there existing, right? So t is not my variable in this problem. This whole function exists. S is my variable. I'm letting that change. How far out do I want to go to get the area? So when I take this guy's derivative, this is easy because the inside function is just s. So who remembers how to do this? This is a very easy example of this. F top 1.
S minus S squared.
Yeah, s minus s squared to the 8th. Just plug s in. And real quick, go with me. Watch. Let's say 8x. What is this integral in, antiderivative terms? Big S f of x. Oh, I'm sorry. Let me make these t's. Sorry. There. Big S f of x minus big S f of. Hey, all right. Stay with me. And that's f top 2 basically with an x instead of a b. We try this again. F top. What the hell's f top? Fundamental theorem of calculus part 2. Says a to b integral is just the antiderivative of b minus the antiderivative of a. That's what we keep doing, plugging these in after we take an antiderivative. That's the process we use. All right, I like it. So what I just did was that. Ooh, that's amazing, Jeff. Well, now watch. I really want this to make sense. So what is the derivative of this going to be? Oh, that's good, Jeff. Let me do it in a different color for you. Slightly different shade of purple. Derivative of this is going to be derivative of that. Well, what's the derivative of big S f of x? Little f. And what's the derivative of big S f of a? What's big S f of a? What is that? It's a constant. So what's the derivative of it? 0. So what did I end up doing? I just ended up putting x into the freaking function. That's all I ended up doing when I took the derivative. So when I take a derivative of something, I just end up putting that in. Done. Because putting that in is just a number. This derivative is going to go away. So it's a really good question. Why do I just end up putting that in there? Because that's what you would do. You're going to evaluate this at that limit, right? I can't explain it any better than that. That's it.
That's f top 1.
That's amazing right there. But say again.
F top 1 is the putting it in, and f top 2 is.
No, f top 1 is this. This is f top 1. The derivative of an integral it basically undoes the integral.
Okay.
The integral of this is something. So when I take the derivative, I come back to what it was. Of course, I undo it, right?
Okay.
So f top 1 is just undoing the integration. The integration symbol went away.
Okay.
F top 2 is this. Get the antiderivative and then plug the limits in.
Okay.
But this explains why this works the way it does. Whatever this is, whatever this function is, wouldn't I plug an s into it? So let's call it big ass t. Wouldn't I plug an s into it? Okay.
Yeah.
If I integrate this,
Yeah.
I get something. Let me call it big ass t. And then I would plug an s into it, and then I would subtract plug a 5 into it. Alright, so what happens when I take the derivative? That becomes this, evaluated at s, minus 0, because that's a constant. That's what I'm saying here. That's why that works the way it does, because that's the way it would work. I mean, There's no other way to say that. That's it. That's the best possible way to say. Anybody in the universe can say that. Yes.
5 over 5 is 18.
5, 5, 18? Oh. So the
Because you would be X, right? You would be X.
definitely not. I really want this. I mean, if you let u be x, du is dx, all you've done is rewrote the original problem now with u's in it. So whatever the issue was is still an issue. You want your u sub to get rid of the issues. So the issue here is I got this division of two functions of x. I don't know how to freaking derivatives of quotients suck. Integration of quotients suck to the fourth power. I mean, it's I don't know if I can. So remember, any derivative rule that seems difficult, the integration of that would be almost impossible. We got to come up with some other way around it. So I want to let u equal what better? Because its derivative is in here. You got to get used to the fact that the square root of x. What's the derivative of the square root of x?
1 over 2.
1/2 x to the. So it's 1 over 2 square root of x. So that derivative is in here. I know, minus the 2, but who gives a shit about constants? I can make them come and go as I want. What I'm talking about is the functional part of it. Yes?
You said the square root of x is u, wouldn't you end up on the bottom anyway?